In January 2018, every major cloud provider on the planet, Amazon, Google, Microsoft, had to quietly patch their entire global infrastructure at the same time. Not because of a software bug someone wrote carelessly, not because someone forgot to update a library, but because of a flaw baked into the physical hardware that almost every computer on Earth had been using for over 2 decades. And the worst part, it had been sitting there the whole time. The vulnerability was called Spectre and Meltdown. And the reason it matters to you, even if you've heard the names before, is what it revealed about a promise the cloud industry had been making to every single one of its customers, the promise of isolation. Here's what you're told when you rent infrastructure from a cloud provider. Your workload runs in its own isolated environment. Your data is separated from everyone else's. The code your application runs cannot see, touch, or interfere with what anyone else's application is doing. You are, in the language providers like to use, a tenant, and your apartment has walls. And for most practical purposes, most of the time, this is true enough. You can't simply reach across a network and read your neighbor's database. The walls are real. But here's the question that Spectre and Meltdown forced everyone to answer honestly. How deep do those walls actually go? Because here's something worth sitting with for a moment. When you run your application in the cloud, even in a dedicated container, even in a virtual machine that's supposedly yours, your code is still running on a physical CPU, a real chip, a piece of silicon. And that chip is almost certainly shared, not just with other customers of the same provider, but between all of their virtual machines simultaneously. The wall between you and your neighbor exists at the software layer, but at the hardware layer, you're in the same room. To understand why this matters, you need to understand one thing modern processors do to stay fast. It's called speculative execution. Your CPU is so quick that it doesn't wait to find out what it's going to do next. Instead, it guesses. It looks ahead at the instructions coming up, makes a prediction about which path the code will take, and executes that path in advance before it actually knows if the prediction is correct. Most of the time, the guess is right, and the work is already done. When the guess is wrong, the processor discards the result and tries the correct path. From your program's perspective, it looks like nothing happened. The discarded work disappears. Or at least, it's supposed to. What Spectre and Meltdown discovered is that even when speculative execution is wrong and the results get discarded, there are faint traces left behind in something called the CPU cache. And those traces are measurable. Not by reading them directly, the memory boundaries still hold, but by measuring how long it takes to access certain memory addresses, an attacker can infer what data was speculatively loaded. This is called a side-channel attack. You're not breaking through the wall. You're pressing your ear against it and listening to the vibrations. And here's why this mattered so catastrophically in the cloud. In a shared cloud environment, a virtual machine running malicious code can use this technique to read memory that belongs to a completely different virtual machine. Memory that the hypervisor, the software that manages isolation between virtual machines, genuinely believed was protected. The isolation was real. The hardware made it irrelevant. Researchers demonstrated that in some configurations, you could extract data at rates of kilobytes per second from other processes on the same machine. Cryptographic keys, passwords, session tokens, things that were supposed to be in a completely different tenant's apartment. I want you to notice something uncomfortable about this. The cloud providers weren't lying when they said your environments were isolated. The hypervisors did their job. The security group rules did their job. The network boundaries did their job. The isolation was real, at every layer that the software could control. What failed was an assumption that isolation at the software layer was sufficient, an assumption that the hardware underneath was a neutral foundation that would faithfully respect the boundaries defined above it. That assumption turned out to be wrong, and this is not a rare kind of failure. It's actually one of the most common patterns in how cloud systems break. Not because someone made a mistake, not because the provider was negligent, but because isolation is never a single thing you either have or don't have. It's a stack of guarantees, each one sitting on top of assumptions about the layer below it. When one of those assumptions fails, everything built on top of it is suddenly less solid than it appeared. That idea, isolation as a stack of assumptions that can individually fail, is going to be the foundation of everything in this series. The patches that came out in January 2018 were genuinely heroic in terms of speed. Google had actually discovered the vulnerabilities in mid-2017 and had been quietly coordinating across the entire industry for 6 months so that patches could land simultaneously worldwide. But fixing a hardware-level flaw in software comes with a cost. The mitigations worked by disabling or restricting the speculative execution behavior at the kernel level, essentially making processors slightly less aggressive in their predictions. For most workloads, the performance impact was small. But for workloads that make frequent transitions between user space and kernel space, databases, certain networking-heavy applications, the benchmarks showed measurable slowdowns. Some reported 5 to 30% degradation in specific scenarios. You paid a performance tax to restore a security guarantee you thought you already had. That's the other thing nobody talks about when they sell you isolation. Maintaining it isn't free, and restoring it after it breaks is even more expensive. So what does this tell us about isolation as a concept? It tells us that isolation is never absolute. It is always a property of a specific layer with specific guarantees that depend on specific assumptions about the layers beneath it. Your VPC isolates your network traffic. Your container runtime isolates your process namespace. Your hypervisor isolates your memory and CPU. These are all real, meaningful guarantees, and all of them are sitting on top of hardware that you don't control, designed by engineers who made trade-offs between performance and security that you weren't consulted about. This doesn't mean you can't trust the cloud. It means you need to understand what isolated actually means at each layer, what it promises, what it assumes, and crucially, where it stops.